inverse trig function lecture. The first part, we talked about what is a sine inverse function. Now, we'll be talking about sine's intimately related cousin, cosine. Recall that something that undoes a function, let's say we have the number 3, then I want to f3. What does that mean? Well, if my f of x is defined to be x squared, then fing 3 is no longer ambiguous. It means I take f of 3 to be defined as 3 squared, which is 9. So now I know how to f3. F of 3 is 9. So what would undo such an operation? So a function that undoes another function is called an inverse function, and we denote it as f inverse of x. Okay? Notice that f inverse of x does not mean 1 over f of x. So since I didn't talk about this distinction in the first part, I would like to talk about this distinction in the second part. Remember that this is not the case. Usually if you have something like x to the negative 1, you can rewrite that as 1 over x. This is okay, okay? But when we do it with function, it's not okay. This is not what it means, okay? It means f inverse of x, in the case of x squared, is actually another function, square root of x. What? How did you come up with that? Well, it's because if f of 3, which is 3 squared, which is 9, then f inverse of 9 is equal to square root of 9, which is 3. Hey, that undid me effing 3. F inverse of 9 gave me back 3. Because when I f'd 3, I took the function of 3, it became 9. So the function that now I can take that of 9 to restore what it used to be, its old value 3, is square root. Square root of that will give me 3 back. So in turn, f inverse of x, if f of x is equal to x squared, the f inverse of that is actually square root of x, because f of f inverse of x is equal to f inverse of f of x, which is equal to just x. This is pre-calculus, and I have videos on inverse functions, and you can go back and look at that. But this very concept is the same concept that governs how cosine inverse and sine inverse work. Let's talk about cosine of some theta. Notice that this is equal to a length, so I'll write it like that. Versus theta. Let's create some entry values. Angle 0, pi 6, pi 4, pi 3, pi 2. Some of our favorite angles, and let's evaluate cosine of theta at our beloved angles here. Okay? Well, cosine of 0 is 1. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 3 is equal to 1/2. Oh, very sorry. Yes, that's true. And then cosine of 0 is 0. So actually, if this stuff is perplexing to you, if it doesn't make sense, take a look at my unit circle video and the video about sine, cosine, and the special values, and it will no longer be confusing. Now, this topic is about inverse trig functions. So let's introduce in a new column the inverse cosine. Cosine inverse of L. And that's because I call it L because cosine inverse likes to eat lengths and spit out angles. So if it eats a length, over here it's going to eat the length 1. Cosine inverse of 1 is what's going to go into this entry. And you guessed it, it spits out an angle and it's going to spit out that angle. So cosine inverse of root 3 over 2, it eats root 3 over 2 and it's going to spit out this angle, pi over 6. Cosine inverse of root 2 over 2 eats this length, root 2 over 2, and it spits out the angle, pi over 4. And as you guys can see the trend, this occurs. And so we can plot this. We may plot this. And when we plot it, this is what happens. So I'm going to erase this information here. So, let's create a plot where our domain is our L and our range is our cosine inverse of that L. Okay? Now, we want to find out what the cosine inverse of L, what is its domain equal to, and what is its range equal to. Okay? Cosine, normal cosine of theta. Okay? Normal cosine of theta, which equals your L, it pops out the L. Normal cosine eats angles and spits out lengths. Cosine inverse eats lengths, spits out angles. So, okay, so our cosine of theta, which is equal to L, it has domain, negative infinity to infinity, and it has range, negative 1 to 1, inclusive. I will tell you right off the bat that the domain is going to be, over here, the same as the range over there. Okay? They're the same. But now, it's not so much the case with here for the range being negative infinity to positive infinity. You saw, as in the first part of the video, that when we tried to extend the sine function, that it would eventually, the sine inverse function, when we extended the sine inverse function, that it disobeyed the vertical line test when we did that. So we had to restrict the domain. Once we restricted the domain, then it was no longer an issue. Okay? So, for it to not fail the vertical line test and for it to remain being the function, we must do that. So take a look. We'll take the length from negative 1 to 1. We know the domain is that. And notice we'll just plot these points at 0, it's at 1. Put a dot. At root 3 over 2, which is right here, it is at the value pi over 6. So we go over here, we'll put a dot. And at pi over 4, it'll be at root 2 over 2. We'll go over here, put a dot. And at, here we go, pi over 3, and pi over 2, we got this here. And so over here, it'll be at the value 1/2. We'll put a dot. And at pi over 2, it touches 0. So far, it looks like a curvy line that goes like that. If you were to evaluate it past these points, so like for instance, the next special angle is 2 pi over 3, okay? How did I come up with that? Watch my old videos. I tell you that the trend is 30, 15, 15, 30 degrees. And so now it's time for 30 degrees addition, and that's the same thing as pi over 6. So we get pi over 2 plus pi over 6 times 3 above. This reduces to 2 pi over 3. That's where we get this next special angle. Okay, so now evaluating the cosine at that, now cosine becomes negative 1/2. And so cosine inverse of negative 1/2, let me put it right here, is now going to split this 2 pi over 3. So if we were to go to these negative values, the rest of the function would look like this. Boom. And it would stop all the way up here. Over here, it would be at pi. Okay? So this is my cosine inverse of L. So it's this curvy line that actually, if I do it again, it's going to look like this. So it curves down like this, and it curves like that. It's concave up and then concave down over here. All right? So we notice that if we go beyond pi, the values would repeat. Okay? Hence, we put the range 0 to pi, inclusive. Because if we go beyond pi, the values, if we keep doing this here and keep doing this here, then the vertical line test would fail. If we were to create a vertical line, it would fail because it would touch it here and here. But if we had just the black part of the graph, which is the restricted range 0 to pi, which is what we want to keep it, then we notice that it remains a function because it obeys the vertical line test. It only touches it at that point. But if you extend it and say, no, the range is all real numbers, negative infinity, positive infinity, why not? Well, if you do that, this vertical line then goes down and it touches here as well. So it no longer is a function, and we want to preserve it being a function. Okay? So this is what our cosine inverse has these properties. It is a function, its domain is -1 to 1, and its range is 0 to pi inclusive. So, now it's no longer as confusing what these cosine and sine inverse functions are, and it's no longer confusing why we're restricting their range. It's to preserve their function properties.